A person with a system will always beat someone without one. This is what my system for descriptive data analysis looks like after 10 years and thousands of data sets analyzed. I feel like I'm having deja vu of deja vu. Welcome, friends and foes, to another Data Devotional, part 2 of our Descriptive Data Analysis mini-series. And today we're going to look at the system that we use for doing descriptive data analysis. I'm Luciano Pesci, founder and CEO of Emperitas and Nexum. We're continuing with the same problem as last time, which is describing data and the patterns that exist in data beyond a single metric. Even with a small data set, tracking is a big problem. You'll be able to see this for yourself with the Silvermint Survey, where 80 metrics can result in 80,000 different tests. My callback to the EDA devotionals was because of this. We're back to the need for a system. And we're talking about the same system. We're continuing on with what we were doing in EDA, which means we will need the same relevant documents, and we should have inspected the data manually and completed all the EDA by this point. And like with the earlier EDA, we're going to be scripting and running analytical output, which means we need a way to organize it all. And my previous advice about maintaining naming conventions and completing the documentation also holds. What will differ here is simply the involvement of multiple metrics. With those multiple metrics, we're after the same kind of information: measures of shape, center, and spread. The term bivariate will mean that we're using 2 metrics, while the term multivariate typically means 3 or more. And when we start to compare metrics, there are 2 broad categories that the patterns we will find fall into: differences and similarities. But what makes DDA a complementary step on top of EDA is understanding the patterns now at a deeper level between the metrics themselves. We'll go even further with this with predictive modeling, but right now we're going to contain ourselves to 2 to 3 metrics. But if you need to understand the patterns across data and you have hundreds or thousands of metrics, that's where predictive modeling comes in. Right now, we're trying to understand the patterns that exist in little groups of metrics inside of the dataset. And we can accomplish that in 2 basic ways, both of which are leading towards automation. The first of these is a programmatic approach, and I will show you an R module next week that will run every combination of 2 metrics possible for the tests of similarity. This is a fully automated approach, and it works very well for tests of similarity and for gray area tests. This approach is not as effective for tests of difference because of the number of combinations involved. For example, if we take the Silvermint survey and its 80 metrics, and we say that we can assume every metric could be compared against every other metric. That's not true, but let's just assume it. That would result in 3,100 combinations, 3,160 to be precise. That sounds pretty reasonable. But if we want to take 3 metrics and look at those simultaneously across all 80 metrics, it's over 82,000 combinations, 82,160. Not so reasonable anymore. Also very cost prohibitive. And because tests of similarity, by their nature, are so straightforward, they're easy for that kind of 2 metric combination automation. Tests of difference, however, do not benefit from random combinations of metrics. They require a specific setup, and they require some thought about what kind of test you're running and why. What evidence is it going to produce for you? And that's the biggest con of the programmatic approach. You will run a lot of output that means nothing and serves no purpose, but it will save you the time from coding. The second of these is the expert approach. And this requires an individual who's an expert on the topic to sort through the data and determine which tests will be run. These are still tests of similarity, tests of difference, and gray area tests. But now, instead of just taking a machine and having it put together every possible combination, you are taking a person who understands which combinations make sense, and that's what you're going to execute instead. The pro of this approach is that you only get what you're interested in. But that's also a con. You only get what you're interested in. There may have been combinations of data that resulted in tests that would have shown you something that you wanted to see, but you didn't think about it. You weren't expert enough. Or maybe you just didn't have enough time. Humans, unlike the machines, have a higher opportunity cost when it comes to time. Which of these 2 approaches you decide to pursue is up to you. I will show you both being applied to Silvermint because we're using both. We're taking a programmatic approach for the tests of similarity, but we're taking an expert approach both for the tests of differences and for the gray area tests, which you'll be able to see in the 2 remaining data devotionals of this little mini-series. Let's connect the problem of tracking hypotheses with their best descriptive analytical tests. Every metric that you're going to use in descriptive data analysis needs to be tracked and defined using the MOST approach: measurement, origin, scope, and totality. Think back to the EDA, and you'll remember that one of the first steps each time was understanding the class or the data type of the metric that you are going to be analyzing. And if you've been building your system for eternity, you can go back to your EDA script and extract all of the information necessary to do the MOST definition formally in a spreadsheet. Context mattered before, but context matters even more now. When you start combining metrics, the context of what the data is telling you is altered, and you have to keep the original context and the alteration in mind, both of them simultaneously. Otherwise, you will make claims that the data does not support. This context creep, where you change the definition of the data slowly over time through your stages of analysis, is very common. If you have the original documents with you, if you are using the most definition, this context will be easy to track and easy to follow, which means you're less likely to make a mistake and say something that the data doesn't support. A new problem that you'll have with DDA that you didn't have with EDA is whether or not the data is connected. Are the fields that you're using connected or are they disjointed? The easiest way to see this is inside the Silvermint survey, where we had different survey blocks for the specific users, which means that in that data file, there are respondents who answered some questions but not others. So we can't run some tests on some of the metric combinations that we would want to, simply because the individuals, the rows, did not see those questions, so there is no answer. Disjointed data will limit your ability to do some of these tests. So the bigger the data sets that you get, the more disconnected they become, the worse this problem becomes. If you can find a key to connect the data, then you can solve this problem, but that's back to the context. Is there something that actually connects them? In the Silvermint survey, in some cases, we have individuals who saw both sets of blocks of questions and did answer. So we can make comparisons, but only for them and not for the majority of those user types who didn't answer both. If you go back to the EDA deliverables for the Silvermint survey, you will see my comments about this throughout the script. DDA is very stats heavy. You are going to run a lot of tests that have a lot of output. Understanding how to parse through that output is important to understanding the conclusions of your tests. If you think back to your stats 101, you might remember how to set up the null and the alternative hypothesis. Personally, I have found that the easiest way to teach this to people is using the metaphor of a legal case where the null hypothesis is that you are innocent and the alternative is that you are guilty. This requires that you go out and collect evidence in the form of data, run tests, and then decide if there's a sufficient amount of evidence to reject the null hypothesis and conclude that you are in fact guilty. In this metaphor, we use the confidence interval as the threshold beyond which we decide there is enough evidence to convict or there isn't enough evidence to show that someone's guilty and to fail to reject the null. Not to say you're innocent, but to fail to convict. We're back to falsifiability. If this is confusing, I recommend that you go onto YouTube and you look for some of these metaphors taught by Stats 101 professors. There are a number of them to choose from. Watch a few and it will eventually click. And it's necessary for it to click because you need to formally state these hypotheses and then track them. Our methods of investigation, to continue with that metaphor, are going to be these types of tests. Tests of similarity, crosstabs and correlation, tests of differences, t-tests and ANOVAs mostly, and then gray area tests in the form of text analysis, principal component analysis, and clustering. Through those tests and their output, we will then step back and decide if we have sufficient evidence to reject the various null hypotheses we set up and accept the alternative hypotheses that we set up. But all of that has to be tracked, which means all of it has to be formalized. Let's solve the problem of tracking these formal hypotheses to their various tests and the resulting output, using the Silvermint survey as an example. This link will take you to a tracking sheet that we've built for the Silvermint surveys DDA using 4 tabs. So the first tab tracks all metrics, that's what you're seeing, and I'm going to go to this in a moment on the screen. The second tab tracks all the tests of similarity. The third is for all the tests of differences, and the fourth are for all the gray area tests. We're looking at the first tab in the tracking sheet, and this is the heart of the tracking sheet, and it will feed what we're going to do in the programmatic approach next time. There are 6 columns. The rows here are the individual data points in the data file, though that's not absolutely correct because this is 4 questions that were multiple select. So like this one here, Q11. I have not listed Q11 sub 1, sub 2, sub 3 throughout, unless it had a sub 98, which is 4 open-ended responses, and that's important for feeding the text analysis. So rather than list them out here, because some of them have many, many columns, this keeps the tracking sheet cleaner, but we'll still be able to deal with it in the automation. But effectively, every column that we're going to use, or every set of columns, if they represent the same question from the survey, are here being tracked as rows. Let's look at the other columns. So we have measurement, origin, scope, and totality, the most definition. Under measurement, we have these different categorical and continuous definitions and the unstructured text. For origin, we have the 3 types: survey, observation, experimentation. For scope, cross-sectional or time series, and for totality, sample or census. Column E is not that useful since column E is all sample data here, but if we were using something where we had additional census data like macroeconomic data that we might be able to link by time to some of the survey data, then we need to indicate that here as being census information rather than sample information. But we're going to assume everything that we're dealing with is sample because for right now it is. Finally, we have column F, which is question type. Because we're dealing with survey data, we need to be able to indicate to the R module whether or not the data point that we're looking at is ordinal or interval. And while we could program that as a hard and clean rule, we're going to treat some metrics that are ordinal as interval, specifically the scaled questions. Technically, we're going to treat them as both. We're going to run them as categorical and then run them as continuous. But we wanted the ability to indicate to the module which type of data it was dealing with based on the survey question, not just on the measurement. Now let's look at the tests of similarity in the second tab. This is a very long list. In fact, let me get real small so you can see it is hundreds and hundreds and hundreds of rows long. And I did build this using my own expert approach. 640 tests of similarity using just 80 metrics. This is why the programmatic approach is so important for tests of similarity. It is well suited to combining two different metrics using simple tests. Something else that's important to indicate when doing DDA, and you'll see this both in the tests of similarity and in the tests of differences, is the nature of dependent and independent variables. There isn't really a dependent-independent nature to crosstabs or to correlation, so this naming convention is just convenient here as a way of tracking which two metrics or three metrics, if I wanted to do a third, you can see column D, that are involved. When we're talking about the tests of differences, and we'll go to that tab, the dependent and independent nature of metrics matters a lot. And it matters in two ways. First, the kind of metrics involved will determine the types of tests that you can select, and which will be the dependent and which will be the independent metric. But a second way that this matters is at the theoretical level. The independent metrics should be things that are independent of the dependent metric. They predict it, they drive it, they explain it. This setup will continue throughout predictive modeling. This setup will continue and grow throughout predictive modeling. So if you're not familiar with dependent variables and independent variables, also known as left side variables, right side variables, predicted variables, predictor variables, those are all names for the same thing. A setup where you as the expert believe these independent things are explaining the dependent thing. But the kinds of metrics that you have involved, whether they're categorical or continuous, whether you have specific numbers of categories, that will determine which of these tests you select. And then you track them here. You set up the tests ahead of time and you track them here. This information was also built through the expert approach. So you're looking at rows of tests. There are only 47 right now, nowhere near the 600 from the tests of similarity. This is why the programmatic approach lends itself well to tests of similarity, especially bivariate 2-metric tests, even 3-metric tests. But when you start to talk about what's called the functional form of the equation that you're trying to explain, with a left-sided variable, a dependent variable, and the right-sided independent variable or variables, now that human expertise matters a lot in setting up things that are reasonable instead of just grabbing everything. Unless you're into machine learning, in which case that's basically the approach. The fourth and final tab here are the gray area tests. So far, I have only been indicating the text analysis that we plan to do. This is for both single questions on the survey, so question 50 was an open-ended text response question, but also for any of the other please specify options that were within a categorical choice for another question. Dimension reduction through principal component analysis and segmentation through clustering are additional gray area tests that we will add here, maybe by the time that you watch this video, that will be tied to specific hypotheses. In that case, what you will see, since there is no dependent or independent nature in some of those tests, is simply a list of metrics that will probably be put in the note. So one metric and then the list of all the other metrics here. Those are details that we're still working on because we will use this tab and all the other tabs for this sheet to feed various forms of automation through the R modules that I will show you in the next 2 devotionals. I mentioned the functional form of the tests that we're running, but you can also mathematize the hypotheses themselves. Whichever of these approaches you decide to take, and I would encourage you to do both, there are tools that will make it pretty easy for you to translate your ideas into math. The one that I first learned on is math type. There are a huge number now of additional options. The first link on this slide will take you to a list of math type alternatives. There are a lot of open source free options. Google Docs has one. You can also use these same tools to translate your hypotheses into formal math. This is an effort that is worth doing, but for a select portion of your tests. I would not run this for every test that you're doing. Instead, I would only produce these outputs when you have a test that you're going to keep. Either way, this is worth the effort because it adds legitimacy and transparency to what you're doing. This marks the halfway point in our Data Devotional mini-series dedicated to descriptive data analytics. Next time I'm going to show in detail the tests of similarity and the tests of differences. This will be through R modules and R scripts and the output. In the fourth and final devotional of this mini-series, I will then cover the gray area tests, also using our same modules, similar output. So keep your own descriptive data analysis progress going by digging into the tracking sheet and familiarizing yourself with the tests that we'll cover in the coming 2 devotionals, and I'll see you at the next ones.